Yes. Hello and welcome, and thank you for showing up to listen to our advanced lecture today. My name is Sandre, and with me I have Meng, Andrew, Miguel, Sungkwan, and Yui. So we have a pretty strong team to tackle this advanced lecture today. As you can probably tell, our topic is multi-agent path finding. And our goal is that by the end of this lecture, you guys have a good understanding about what this topic is about, and really how to approach and solve the multi-agent path finding problem. And if you have any questions throughout the lecture, just feel free to ask them at any point. And if you don't want to ask them in the lecture, you have allocated some time at the end of the lecture where you can ask questions. And yeah, we're multi-agent pathfinding group number 1, because there is another group, the next group, that also does multi-agent pathfinding, but they use some different assumptions and a different approach than what we do. Okay, so I mentioned the multi-agent pathfinding as our topic, and then I went on and mentioned the multi-agent pathfinding problem. And that's because multi-agent pathfinding really boils down to solving the multi-agent pathfinding problem. So the question is then, what is the multi-agent pathfinding problem? And I'm going to describe that by using a pretty straightforward example. Suppose you have 3 robots, right? They live in the world and it's a good time and everything, but what they really want to do is that they want to get to the goals. And the multi-agent pathfinding question is then, how do these robots get to the goals in an optimal way with avoiding collisions? And that's really it. You have a bunch of robots or agents, they want to get somewhere and you don't want to crash. I think it's pretty straightforward actually. And we are going to give, if you don't understand this yet, we're going to give a more formal mathematical or definition of the problem later. But given that that's fair, we have a problem, the question is then, why do we actually want to solve this? And I'm going to kind of try to give the intuition why this problem is important by showing a couple of videos. Yeah, the first video here is from Amazon Robotics. Many of you guys have probably seen it before, and I'm actually just going to start the video so we can have a look. It's not the most interesting thing in the world. Many of you guys have probably seen something similar before. But the takeaway here is really that this is like warehouse automation, and it's a pretty common thing to automate nowadays. And even though the goal is warehouse automation, multi-agent pathfinding is a pretty crucial part of this system. You have a bunch of robots. The area is like pretty, what do you call it, sparse. There's obviously sparse. There's not a lot of space. And you need to have a way to coordinate these robots so that they get to the goals without crashing. Another, maybe a little cooler example is this one. Did any of you guys watch the opening ceremony to the Winter Olympics? Did you guys see I see some heads doing this. Did any of you guys see the light show they had going on? That's good, most of you did. For those of you who didn't, I'm gonna show a pretty fun video, I think. Yeah, as you can see, it's a bunch of lights doing animations in the sky. And what it actually is, it's a bunch of drones working together, creating these visualizations. I think it's clearly a part of this problem as well, that multi-agent pathfinding is important. And I think it's actually pretty crazy, and that multi-agent pathfinding is a important part of what is actually art, right? So high-tech art, I guess. Okay, so I have one last video, and this is actually my favorite one. And I don't think many of you guys have seen this one before, so I'm gonna start it, and I think I have subtitles on, so you guys have to read those.
We have stored things in shelves forever. It's natural to us. We want things to be within an arm's reach. Robots, on the other hand, shouldn't have to. They shouldn't need rows of shelves or long walkways. So why waste time on shelf-based solutions when AutoStore is here? AutoStore is a cube-based system, making use of all space for proper warehousing. Turn that wasteful air into storage and double, triple, or even quadruple the inventory capacity without moving to the building. Bins are stacked right next to each other, on top of each other. Radio control robots drive on tracks above the cube. Lifts down to grab bins and deliver them to workstations for order fulfillment or replenishment.
Yeah, have anyone seen this video before? At all? Ever heard about it? I think it's pretty cool. It's basically just an alternative to warehouse automation. And why I'm a big fan of this video is that you can, I don't know if you can tell by my accent, but I'm not from the US. I'm actually from Norway, a pretty small country in Northern Europe. And more specifically, I'm from I'm from a small town on the western coast of Norway. And most of the industry, almost all of the industry is fishing. That's basically what we do. But we have this one high-tech company, and that's this company. And I think it's pretty cool that, for me, like motivating that even though you live in a small town Norway, you can create a pretty cool company that actually competes globally with Amazon Robotics, which is really motivating. I think these guys, they set in 2017, they set a sales goal, the amount of systems they wanted to sell before the year was over, and they reached the goal in early February 2017. So it's pretty booming industry right now. A lot of interesting stuff going on, and well, the giveaway here is that, or the takeaway is that multi-agent pathfinding is an important part of the multi-agent systems. So the reason why we want to do multi-agent pathfinding is really the reason, kind of reduces to why do we want to do multi-agent systems, right? And clearly, multi-agent systems, they increase efficiency, as you have seen. They offer more flexibility, and they offer more redundancy, right? Like if one of these robots on the AutoStore grid, if one of them crashes or breaks down, then one of the other robots can kind of take their job. And in the end, it just looks really cool, right? Having multiple robots working together, it just looks cool. Okay, so hopefully by now you guys have some intuition about why we want to solve this problem. And we're not just going to talk about the problem, we're actually going to go ahead and solve it. And the way we're going to do this is that we're going to give you guys actually 3 different algorithms where each of the algorithms, they differ from the other ones in their own way. And before we do that, we're going to start off by introducing the problem a little more formally, and we're also going to introduce A-star, which is a pretty common algorithm in planning. And I'm going to give that to Andrew.
Thank you, Sandra. So yeah, as you said, basically we're going to start with going a little bit more technical into what the definition for the map problem is, and then go through A-star, just do a quick review over that, so that we can then look at the simplest way to solve a multi-agent pathfinding problem, which is using the A-star search. So yeah, the first thing we're going to do, just briefly recap. Sandra did a pretty good job of explaining what the multi-agent pathfinding problem is. Essentially, the core unit of the problem is the agents, which in this case are just our robots. Each robot has a predefined starting state and a predefined goal state. There are multiple agents, that's the name. Each of them are trying to get from their start state to the goal state without ever colliding with each other. At every time step, any of these agents can move to adjacent vertices on the graph. We'll go a little bit more into detail about how we transform the state space into a graph. But yeah, they could either go to adjacent vertices or stay put. And most of the common solutions for the multi-agent pathfinding problem are based on A-star. So for that reason, we're going to do a very quick recap on how A-star works, and then go to solve the math problems with A-star. So just quick recap, A-star is based off of, well, it's a search algorithm based off of best first search. So you guys might remember a little bit about how this works from when we did like the enforced hill climbing searches. But basically, the idea is you have some starting state, and then you want to eventually get to the goal by expanding states. The way that you choose which state to expand is by which state has the best score based on some like heuristic or function. And expanding just means looking at all the neighbors and then figuring out which one to go to next. So A-star is just a specific version of best first search that uses the following functions defined here: f equals g of x plus h of x, where g of x is the cost of getting to like the current state, like the actual cost going along the edges. And h of x is a heuristic that tries to underestimate the cost of going from that state to the goal. So if you see like the example here in the corner, basically you start at the start state, and then like everything starts, you go to A first because it has the lowest cost, and then expand to B because that either has the lowest cost of A's, and then realize that D is actually a shorter cost of A, so you start going the other way, and then it continues to expand until it eventually reaches so does that all make sense? I don't want to spend too much time because I think everybody's got like a decent understanding of how that search works. So the neat thing though is that we can pretty easily formulate the math problem as an A-star search. Like usually people use A-star to do like searches for just one agent or one robot at a time. But you can actually use it to just solve the math problem as is, and the way that you do that is by just representing the states in a kind of unique way. So let's say we have a graph with k agents and v vertices. The states are just all the ways to place those k agents in the v vertices at any given point in time. So the way that we can kind of represent this is just a list of lists where each inner list corresponds to like the current state of the current coordinates of each agent. And the goal is the same thing, but it always just maintains the goal for a corresponding agent, the corresponding to that. And the way to calculate neighbors is just all of the possible lists that can be formed from like each of these agents moving to either adjacent vertices or staying the same. So that's a very large number of possible lists that can be formed. So there's a lot of neighbors at any point in time. We'll go a little bit more into detail about how that works. The other thing to keep in mind is that agents can move concurrently, so it's not like we're just having one agent move at every time step. They're all moving at the same time. So let's do like a really quick example. If we just have two agents, the start state is just the coordinates, and we want them to go back. So if we're doing A-star, we want to expand the first node, the first state, which is just the start state. And to do that, we can look at all the possible moves that can happen here, right? Each robot can either go up, diagonal to the right, or go down, or they can stay put. So each robot has 4 possible moves, and since there are 2 of them, there's possible like 16 combinations of 4 squared, or 16 possible neighbors. So what we do is we just start looking at each neighbor and start adding them to the priority queue by calculating the function that I defined earlier. So the first one, we look at the first state, is just both of them staying put. We're not going to add that because that state's already been expanded. We go to the next one, which is like the bottom robot, maybe moving right. Calculate its cost and see that it's kind of high because actually we want the robot to go that way, remember? Then we look at the next neighbor, which is the bottom robot going diagonally. In this case, that's actually a lower score because it's going more in the direction that we want it to go, so we actually add it to the front of the priority queue. And we just continue this pattern until we've done it for all of the neighbors. One thing to keep in mind is that we never add collisions. So when we have something like this where they're both going to the middle, we're actually just going to not evaluate that and do calculations for it because it's not a possible state. So yeah, we do that till the end, and then eventually we pop whatever's in front of the priority queue, and we repeat that process over and over again until we reach the goal. So the big question here is, does anybody see a problem with using this kind of a search to solve the math problem? I think yeah. Huge number of states. Yeah, exactly. So the big issue with using just A-star to solve a multi-agent pathfinding problem is if you have like a branching factor of b, the multi-agent pathfinding, like the graph alone has that, then the multi-agent pathfinding problem is branch factor b to the k, right? We saw that with just 2 agents, like each state had 16 possible states, and that they were already in the corner, so it's actually could possibly be more depending on how big that graph is. So an example, if there are 20 agents, each with 4 possible moves, then there are 4 to 20 possible neighbors, which is just not reasonable to actually do. And this gives this is kind of the motivation for all of the algorithms that are going to be explained later or next, because they were all trying to find more efficient ways to solve the multi-agent pathfinding problem. Specifically, is the influence for conflict-based search. So Meng is going to explain that one next.
Thank you, Andrew. So my name is Meng. I'm going to introduce the method called conflict-based search. And as Andrew, so here is the review of the 9 grid problem that Andrew has talked about, where we have a right region and a red circle and a green circle, where red circle is going from here to here, and the green circle is going from here to here. Well, you can see if you're going straight, then there's a collision, there's a boom. And well, we define boom as a conflict. Well, the formal definition of conflict is if you have more than one agent appear at the same location at the same time, we don't allow that. So our objective is to find solution with no conflict at all. And the problem with A-star approach, as Andrew has introduced, where you can see that if we allow the agent to move straight and diagonally, then for each agent there are 4 moves. And on the table on the right, you can see that it's almost like a permutation, or it's a large number of combinatorials. And if we solve everything at once, we basically run out of memory. So it's not a feasible solution to solve many agents at the same time. So that's for us the way to find a way to reduce the amount of memory that the algorithm will need. So from A-star, we can recap the steps we used. We solve one time step at a time for all the agents, and we check if there's any more than 2 agents appear at the same time, same location, and repeat that until all the agents reach the goal. And how do we reduce the memory from this? Well, maybe we can look at it from another perspective. So this is trying to avoid conflict. But what about if we try to resolve conflict? So if I just give you a basic outline of the algorithm, can anyone fill in the blank of that page? So here we try to solve some solutions for all agents. We check conflicts, and we somehow add constraints, and we repeat that. So the difference from the 2 algorithms: one, we try to avoid conflict. The other one, we try to resolve conflict. Anyone has any idea? Yes?
So this we just treat each agent independently, and then we get a path for each one of them, and then we then check to see if those paths have conflicts.
Do we solve path incrementally, or do we solve all the paths at once?
So all the paths that work for all the agents, and then check the conflicts.
That's correct. That's correct. So we solve 4 solutions for all agents. So we don't expand steps incrementally. We solve all the solutions for all agents, and once we have the complete set of solutions, then we compare from conflicts. And from here we will introduce. This is the concept of constraint tree, and we are going to use this algorithm to solve this problem again, where we can decompose the 9 grid problem into 2 separate problems. One is the red agent going from here to here, and the green agent is going from the left bottom corner to the right. And the first iteration, we're trying to solve the optimum full solution for the red agent. Well, apparently it's going straight. So it's going to go from position 2, 0, 1, 1, and 0, 2, 1, 1, and 2, 0. And similarly, if we solve the solution for the green agent, it's going to straight as well. So it's from 2, 2, 1, 1, and 0, 0. Well, you can see that there's something wrong with it, right? So it's appearing both agents, the solution here give you the same location 1, 1 at same time step. So there's a boom. and we try to resolve that. So in trying to do that, as we already discussed, we put a stop sign over here, and this stop sign only applies to the t equals 2, which is when the two agents appear at the same location. And similarly, we apply a stop sign over at that location at t equals 2 as well. So in that case, we have decomposed this problem. We solved that individually for all the agents, and we found there's a collision, a boom. And we can decompose this problem into where you solve this problem where you have a stop sign at t equals 2 only at the time, and when you allow the green circle to move freely. And similarly, you have a red agent where you allow it to move freely, and the green agent you basically add a stop sign at a certain time step, and the time step is where the collision happens. So in this case, it's t equals 2. So if we solve this problem again, we can see that this solution really depends on the heuristic functions you define. But here is just a basic example. The red agent decides to stay here for one time step and go straight, and the green agent just moves directly to its destination, and there's no conflicts here. So we found a solution. And similarly, when the red agent is allowing to move freely, we found there's no conflict as well if you solve in a similar way. So this is a basic demo is what happens. Again, so the choice of heuristic functions will largely influence the path that is found by the solver. For example, in this case, both agents decide to wait for one time step, but it doesn't have to be the case. If you really punish the waiting for the agent, it will rather move somewhere than just staying there. But if you don't punish waiting and you try to minimize the total travel distance, it'll prefer to stay in its original location until the conflict is resolved. Any question at this point? Great. So let's recap what we did. We solved single agent path finding problem without worrying any conflicts, and we find conflicts among agents. Then we put artificial stop sign at certain time steps where the collision happens, and repeat both steps until all the conflicts are resolved. Yes?
So the stop sign just needs to wait.
It doesn't have to be wait. It could be an artificial obstacle, or the agent can't wait. But this thing only appear at that time step. At other time step, there's no restrictions for the agent to move.
So do you run a star again to get around this obstacle, and then sometimes the solution is to just wait?
Yes. Yeah.
You do.
Yeah. So
Okay.
A star, remember, is a priority queue, right? But then how it chooses results is going to depend on the heuristic function, right? So if you don't punish waiting, then this agent will probably stay there. If you try to minimize the total distance traveled by all agents.
Okay.
Yeah. Any other questions? Great. So here's the overall architecture of constraint tree that we just discovered together. So a constraint tree consists of 3 elements. One is the set of constraints for each agent. For example, the red agent and the green agent with that stop sign over there, and the solution for each agent, which you solve using a star or best first search solver, and then the total cost for the counter solution, which then you again evaluate the cost of that strategy and determine if that is the minimum one you can find. And here you can see there's a higher level solver where you maintain a constraint tree and assigns constraints for the single agent path finder, and then using that single path finders, we return the ultimate path for each single agent back to the constraint tree, where it manages the constraints again for each agent. We are going to examples again for this one. So if we define a conflict as if there's two agent, one is AI and JJ, occupies vertex V at time step t, and put into the context of our 9-grid problem, where we have a boom over there. The conflict will be a boom again, and red AI will be red circle, and AJ will probably be the green circle, and you can interchange that in this case. And if we define constraint as AI can be, you avoid AI from being at vertex V at time step t. In the context of 9-grid problem, that is a stop sign. Constraint is a stop sign where AI is probably one of the agent, probably red or green. And this is the overview of the constraint tree, where the first node you don't have any constraint. So if both two agents are moving freely as a straight line, and the square, the red square, basically highlights the conflict, and then you assign constraint to the this is where we decompose the problem into two separate problems, where one problem has the constraint preventing either the red or green agent from moving to the middle at the time step 2, and then you solve the solution and find the optimal solution. Any question at this point? All right. So one question: is this algorithm guarantees optimality? Any thoughts? Is it yes, or it could be either yes or no? Can anyone make a guess?
Theory of lectures, no.
Why?
Well, my theory of lectures has been okay.
Excuse me?
So, I mean, okay, so for sure, so there's a lot of friction that's happening here, and like just adding these constraints doesn't guarantee they're necessarily getting, in that sense, you're just getting something that's not going to us.
He has a point. Anyone disagree with him? All right, I disagree with him. It's actually, it guarantees optimality. Why? Well, you said if you solve these two solutions, right, it has no conflict, right? But you said it doesn't guarantee optimality in that case. But remember, we add constraint to both cases, right? We add constraint to red agent and green agent as well for two separate problems. And here we get the same cost 5 and 5, but maybe we get different costs, right? In this tree case, right? So if this cost is lower than that one, we're choosing this one. So in this case, we are basically maintaining two priority queue. One priority queue for the single agent pathfinder, where it finds the optimum path from the starting position to the goal position. And in this case, this priority queue, we maintain a list of the lowest cost situation that we find. So in this case, you can probably prove it by induction, but this is like a more visual case where you can see that this thing guarantees optimality. Anyone disagree with me? Good. So now we're trying to go to a more general case where we try to abstract the constraint tree idea. Assuming that we have a conflict AI AJ again, and we're starting from no constraint, so there's an empty set. And again, there's a conflict AI AJ, so we assign AI with a constraint and AJ with a constraint. And you can compare the constraint tree over on the right, and in the context of the 9-grid problem. Any question? Yes.
Can you talk a little bit more about your cost function?
Yeah, cost function can be basically any cost function you define, and two common cost functions is one, minimize the time span of all agent from starting to move, and the last agent from stop moving, and one is you minimize the distance being traveled for all the agents, right? And you can probably define other heuristic function as well, where maybe you want to punish the waiting time or not. It's really just the choice you make, but that will totally that automatically influence the behavior of agents when solving the problem. Okay. So in trying to maintain optimality, we not only assign the constraint to one agent, but both agents. This is the two-agent scenario, and you can put that into the context of the line-gradient problem. Now, what if we have more than two agents? Well, following the same idea, we assign the constraint for, like, maybe we have three agents, AI, AJ, AK, all appear at vertex V at time t. Well, at each node we only allow one agent of moving freely, and the other two we put a stop sign. In this case, probably there are three choices. One is we allow AI to move freely, then we're left with AJ and AK from not moving into vertex V at time t. And similarly, we have AI, AK, and AJ, AK. And in general, if we have K agents, then we are basically growing into K children, but with each one, we have K minus 1 agents in that constraint. Is that clear? Okay, we're moving on. So, well, this is a K-way tree, and in terms of when you are trying to code it, it will be probably not not the easiest one to code. So we tend to convert it into a binary tree. And you can see that the same expansion problem where we have AI, AJ, we have the same conflict, and in this case we assign K children, but in that case we only grow into two branches at the same time. So how does that work? We will only expand the first conflict that we find. Remember in the previous case we have two conflicts, right? And in this case, once we find the first conflict, we stop and we expand from there. And in this case, AI will basically become AI AK. And there's something interesting over here, because these two children have basically the same constraint. If we have the same constraint, do they yield the same results? Yes? Right? So there's no point of solving the same node over and over again, even if they are, well, in this different node. So we want to reduce the cost somehow by tree pruning. So in this case, if you have this 4 children, you should only solve 3 children in this example, because the middle 2 are the same. Any question at this point? Great. And this is a 4 agents problem for the 9 grade problem. You can see that it's a 4 successfully find the solution. So let's go over this idea again. So we start from the original problem where we can decompose it into a 2 individual problem for each agent, and we find a conflict, and then we add a constraint for each agent and solve the problem again, and until there's no conflict. And it greatly resembles one of the activity planning concept we had during our lectures, and that is the goal regression activity planning. And the general idea is that if you have why is A star difficult to solve? Because you are meeting a long list of that, and it's basically a large combinatorials. For this case, we are not adding combinatorials until it is needed. So that's why this one is easier to solve, and it's actually a general paradigm or general strategy that's been applied in many cases. And in the P set, you'll be asked to find a similar algorithm that resembles this strategy, and maybe you can use that one, or maybe you can come up with something else. I'm basically giving you the answer. And also, here we maintain a two higher and lower level constraint or solvers. The higher level solver maintains the list of constraints, and lower level solver give you the single agent path solutions. And let's evaluate this strategy at the very end. When does this strategy is most effective? Well, it's when there are not so many conflicts. Because at every tree expansion, you solve the solutions for all agents again and again. right? So if you have to solve it for many, many times, it's actually proven to be less efficient than the A-star algorithm. But if you have less conflicts, or if you have a large spatial domain with fewer agents, then there will probably be a lower number of conflicts, which in this case is actually a very superior algorithm to use. So in the Amazon case, which Sandro has showed you, where you have a million agents moving around, in that case, this algorithm probably will make Amazon bankrupt. But in that case, you probably will introduce you other algorithm which will be demoed by.
Thanks, Mike. Alright, so here's a reference for the paper for subdimensional expansion in MStar. Alright, so once CBS or conflict-based search came out, people started to think of ways to improve it. They felt that they expanded unnecessarily some cases, that there was a lot of issues with it. So that's where the concept of MStar or multi-agent star is what we think it means. If we don't explain what MStar stands for. And subdimensional expansion come in. So the idea is that you only expand when you absolutely have to, when there's a conflict. So the algorithm in itself, the paper, is very dense and there's a lot of concepts that are complicated. I'm going to simplify it, I'm going to go through an example, and I think that that'll explain how the algorithm actually works, and I'll go into some concepts that are relevant for the design. So here's a really brief overview of how the algorithm works. So before you start, you need to calculate an optimal policy for every robot, from every state to a goal. From that, you start following the policy. If there's a collision, you move back one step, consider all possible states that don't cause a collision, choose the one that minimizes the global cost, move, and repeat. Alright? So let's first talk about the example. This will be the state space. The columns will be defined by letters A, B, C, D, and the rows 1, 2, 3, 4. So now let's talk about finding the optimal policy. For anyone who has worked with MDPs, Markov decision processes, the idea of a policy is very similar. It's a deterministic form of that. You're basically trying to find an action to take at every single state that'll lead you to the direction of something. In this case, our goal. So let's say that we have a goal at D4. How can we calculate the policy? Anyone have any ideas? No. I can give one idea, if someone else wants to give the other one. So one idea is that you start at the goal, and you try to find a path to every other state, and then you invert the edges, right? That's starting at the goal and going backwards. Can anyone think of another way to do that? Yeah.
Start at either random points or edges, and then also visit points that you haven't hit internally.
Yeah, exactly. And in fact, that's the choice that they make in the paper. They talk about going through random points, finding a path to the goal, and using